All right, good afternoon, ladies and gentlemen. It's very nice to see all of you, the full lecture room. I also welcome everyone who is connected online. My name is Tomáš Vejchodský. I am the director of the Institute of Mathematics of the Czech Academy of Sciences. And it's my honor and pleasure to welcome all of you at this Eduard Čech representative lecture of our institute. We organized this lecture since 2004. The first lecture was given by Jaroslav Kurzweil, followed by another prominent Czech mathematician, Miroslav Fiedler, and then followed by distinguished mathematicians as Jean Maven, Ivo Babuška, Gilles Godefroy, Vladimír Šverák, Willy Jäger, Hans Triebel, Vladimír Souček, Wolfgang Wendland, Jean-Pierre Bourguignon, Camilo Delelis, Jiří Outrata, Giovanni Galdi, Vojtěch Redl, Stevo Todorčevič, Antonín Novotný, Rama Mohan Paturi, Yoshihiro Shibata, and today the Jubilee 20th Czech Lecture by Professor Samuel Bas. Before we start with his lecture, I would like to say a few words about Eduard Čech. Okay. Eduard Čech lived in years 1893 to 1960. In 1912, he started to study mathematics at the Charles Ferdinand University here in Prague, but he had to interrupt his studies at 1915 during the World War I and his military service. But after the war, he managed to get back to his studies and finished it. In 1920, he became Doctor of Philosophy. Shortly afterwards, he received stipend to spend one academic year in Italy, where he cooperated with Guino Fubini. And when he came back from Italy, he received a professor position at Masaryk University in Brno, where he spent almost 20 years. In 1935, he was invited to Moscow to a special conference on combinatorial topology. And his results in topology attracted quite a great attention there. And thanks to this attention, he was invited to Princeton, where he lectured at the Institute for Advanced Studies. So that was a great success for him. After he came back from United States, he founded a topological seminar in Brno. It was in 1936. This seminar was very productive. During 3 years, they produced 26 research papers. In 1939, the Czech universities were closed, but the activities of this seminar continued. Eduard Čech, Josef Novák, and Bedřich Pospíšil, the main representatives of this seminar, meet in private in Pospíšil's apartment until 1941, when they had to stop because Pospíšil was arrested by Gestapo. After the war in 1945, Eduard Čech moves back to Prague and enters Charles University. In 1947, he is the head of the Research Institute for Mathematics by the Czech Academy of Sciences and Arts. This institute was in 1950 transformed to the Central Mathematical Institute, and Eduard Čech was its director. And this institute was further transformed in 1933 to the Mathematical Institute of the newly created Czechoslovak Academy of Sciences. And this is the date when we consider the beginnings of our institute. We are the direct followers of this Mathematical Institute of the Czechoslovak Academy of Sciences. And Eduard Čech, of course, was the first director of our institute. In 1954, Eduard Čech moves to the Charles University to the newly created Faculty of Mathematics and Physics. So this was my brief introduction of the great Czech mathematician, expert in differential geometry and algebraic topology, Eduard Čech. And now I would like to ask Pavel Pudlák to introduce our today's speaker, Professor Eduard Bas. Pavel, please.
Hello, colleagues. It's a really great pleasure for me to introduce this year's Eduard Čech Lecture, Sem Bas. Sem Bas graduated at Princeton in 1984. Then he spent 2 or 3 years in Berkeley as a sort of postdoc. I don't know whether it was called postdoc back then. And then he got a position at University of California in San Diego, and he has been there since, now as a distinguished professor of mathematics and jointly a professor of computer science and engineering. I first met Sam in Manchester on Logic Colloquium in 1984. It was about the time when he graduated, and he arrived with a pile of copies of his PhD thesis. And I think I got one of, back then, one of these theses. Definitely I had one, but it has disappeared from my shelf as all the books tend to disappear, and the shelf is full of junk. And okay, so then we started a real cooperation in the 1990s when it was possible to apply for international grants, and we formed a group of people from our department and several people from the US, but mainly from San Diego, which included Sem Bas, Russell Impagliazzo, and there was also Tony Pitassi and Peter Claude from other universities, but a very important person was also Gaisi Takeuchi, the famous Japanese-American logician. So Sam is working mainly in logic and theoretical computer science. His range of interest is very broad, but he's mainly working in proof theory, where he's well known, and in complexity theory, but his interests include also computer graphic. He's probably most known for introducing what he coined to be bounded arithmetic, which is a formal theory that is intended to capture reasoning using low complexity notions. But today he's not going to talk about bounded arithmetic, but about another topic in which he's been working, and this is satisfiability. And I let Sam to explain you what is he working on.
Thank you very much, ladies and gentlemen, Professor Samuel Bas and his 20th Eduard Čech Lecture. Welcome.
Okay. Yes. All right. Good. So thank you again. Sorry for the getting set up. Pavel gave a very nice introduction of some of the early days of my connection to Prague. Actually, I'm reminded that it goes back a little further even than Pavel knows. When I was a graduate student, approximately 1983, I was working on topics of logic and P versus NP, and my advisor, Professor Kochin, was a little dubious about this as a thesis topic. And I found a paper by Professor Petr Hayek, who some of you may know, who had written about P versus NP and set theory. And I showed this to my advisor, Professor Kochin, and he said, yes, it sounds like it's okay to work in this topic. So this is how I got my professor's blessing to work in the topic. Pavel mentioned our joint grants here, which I was going to also talk about, but he's already talked about it, so I won't say much more to say. But here's a list of the people that we worked with. And I did, however, get some photographs from the time. My first visit to Prague was 1989, and somehow we didn't think to take pictures. But the next year we were all in San Diego, and it's hard to see here, but Pavel was here, right behind Professor Hayek, who's right here. Jan Krajicek is off to the far right side, and Professor Takyudi is holding the red binder in the front row. I'm next to him there. We met a few years later in Luminy near Marseille at a conference in honor of Geisy, and here's more pictures of us here. Professor Hayek, and so you should be able to see it here. Let me see here. Get the right. They changed things around on this too. Yeah, so right here, you'll see, let's see, here's Professor Hayek. Here's Pavel. So we were getting together. And then a few years later, there was the Logic Colloquium in Prague in 1998. You can see us there. And Professor Hayek is there dead in the middle. He was the local organizer. Pavel is over here to the side. And of course, many other people are there, but they're too small to see. I'll post this online, by the way, if you want to try to zoom in and see more of this. So, but at any rate, I'm very grateful for the collaborations over the years, and I've visited here quite a few times over the years. So today I want to talk about satisfiability solvers, and in particular, the relations to proof systems and to trying to make satisfiability solvers use stronger proof systems known as extended Frege proof systems or extended resolution. So just to say a little bit of background, I know not everyone has background on these things. Satisfiability solvers are, first of all, they're very important for theorem proving at a low level nowadays. They're also extremely successful. They deal with propositional formulas where, although satisfiability is NP complete and thus deemed to be very hard in general, these SAT solvers routinely succeed in solving problems with hundreds of thousands or even millions of variables. And brute force search would be like 2 to 100,000 trials or whatever, which of course would be completely out of bounds. But for the types of problems that come up in many situations, they're very successful. So it's really quite remarkable. And I'll talk about that some, and then I'm going to talk about two methods of trying to extend satisfiability solvers towards stronger proof systems. The first one is DRAT and I lost my pointer here. DRAT and propagation redundant proof systems. And the other one is a very recent proposal of mine and some co-authors on dual implication points that I'll talk about near the end. I probably have plenty of material for the talk, so you may as well stop me in the middle with questions if you wish, rather than saving everything towards the end. So anyway, so feel free to speak up. So again, just to say what a satisfiability problem is, you're given a formula over Boolean variables that take on true-false values. They're joined together with connectives like and or and not. And you're trying to find whether there exists a truth assignment that makes it true. We'll deal with sets of clauses, which means formulas that are in conjunctive normal form. They're ands, of ors, of literals. A literal is either a variable or a negative variable. And this question of satisfiability, as I mentioned, is NP complete. So NP complete means that, of course, it's, first of all, it's conjectured to be very hard to solve in general. But the nice thing here is that it's not only NP complete, but it's NP complete in a very efficient way that many of the standard NP complete problems, such as traveling salesman or graph coloring and so forth, are all efficiently reducible to SAT. So if you gave an efficient algorithm for SAT, you would immediately give quite efficient algorithms for a wide range of NP complete problems. And just to state an example theorem here is if you look at the question of a non-deterministic Turing machine and you ask, does it accept in k steps? You can transform that into an instance of satisfiability that has k times polylog of k many steps or quasi-linear size. So the transformation from question of whether a Turing machine accepts in k steps to whether formula is satisfiable is not an excessively big transformation. So if you could solve satisfiability efficiently, you could solve these types of questions, which are very general. And as I mentioned at the bottom of the slide, there's many applications of satisfiability, including combinatorial theorem proving and so forth. So, okay. So how do satisfiability algorithms work? So the usual, most general method, there's quite a few methods, but the most general effective method is what's known as conflict-driven clause learning. The core methods for conflict-driven clause learning are the following. You pick one of the variables, you set it either true or false. You then set all immediate consequences that follow by unit propagation, which maybe I'll come back to what that means in a moment. But it's a very simple way of looking at what spreads from that consequence. You repeat that for as long as possible until something's falsified that shouldn't be falsified, and then you stop. And at this point, you've reached the reason why you can't set the variables in this way. You infer a new clause, and a clause is a disjunction of literals, and you add that to the clause database, and you backtrack at least partway back through your setting of assignments and try again. And so this is basically what conflict-driven clause learning is. It's very simplistic as a high-level point of view. And as I said, this is the core of the method for solving these instances of SAT very efficiently. There's a lot of things that get added onto this, including restarts, where you totally restart the depth first search, deleting clauses at various points, and so forth. There's a lot of important heuristics, but this is the core of it. So this corresponds to more or less the proof system of resolution. So resolution, I've drawn here, is the following proof system. You start with clauses, and the goal is to show that this is a CNF formula, and a clause is a set of disjunctions. The goal is to show you can't simultaneously satisfy all the clauses by assigning the variables true or false. And you use this one type of inference rule from C or X and from D or X, D or not X. Now, right, overline X means not X. So if both C or X hold and D or X hold, then you know C or D must hold. Because X has to be either true or false, so either C holds or D holds. If you can use this type of inference to derive the empty clause, which can't be satisfied, then you know that your starting set of clauses can't be satisfied. So a simple example is here. If I get my picture out of the way. Oh, nice. Okay. You can see me, you don't need my picture. Is here, there's three clauses we start with. X, and not X or Y, and not X or not Y. The claim is there's no way to set X and Y to true false to make all three of those true. Well, to infer this with resolution, you can start with X and X or Y, and sorry, you start with, I feel like something's wrong there. Missing some not signs. I'm missing some not signs. That's what's wrong. Oops, that's not a not sign. Sorry, wrong button. Right. You start with X, and you would start with not X or Y, and you infer Y. And on the other side, you start with X, and you start with not X or not Y, and you infer not Y. And then from Y and not Y, you infer the empty clause. Okay. So that's how you would refute a simple thing like that with resolution. And I should probably say how unit propagation works as well, just sort of say that in words. If you start with, say you start with unit propagation, suppose for instance, you set X to true, right? Well, if you set X to true, that'll tell you that since not X or Y must be true, that Y must be true. So that's an example of unit propagation. I've set every literal in the clause except one to false. The remaining literal must be true. So if you set X to true, it follows that Y must be true, and then similarly it follows that Y bar must be true, and those two things conflict each other, and you get a conflict. Okay. From that, you would then learn the clause that X has to be false, for instance, and I'll give you more complicated examples of that. So that's basically what's going on with resolution. And it's known that if you're allowed to do the restarts, at least, that resolution and CDCL have the same proof strength, which is good news and bad news. It says CDCL has a certain amount of strength, but on the other hand, resolution is known to be a very weak proof system, so that's a little bit disappointing. Okay. So the real situation's a good bit more complicated than the simple one I just put on the last slide. So here's an example of what the real situation looks like. So I've got a literal X here. Maybe I'll just leave it permanently on here. Here's what's known as a decision literal. I've set X true. Earlier, I set A, B, and C true. And now I've come along, I've set X true. Now there's a bunch of clauses present. So for instance, here's the clause not X or not A or Z. And X is true and A is true. So that tells you that Z has to be true. And next there's the clause not X or Y, not X or not Z or Y. And now I've just shown that X and Z are true, or assume they're true. So I get Y is true. And I repeat this process. And then in this particular case, I end up with a conflict, right? I've violated, the last clause was, should be not, oh, here it is. The last one made false is here at the end, not T or not B or not W, right? So I've stepped through the process and made everything false. So we analyze this graph, and you'll see this dotted line is here, right? This dotted line there. That dotted line is picking out what's known as the first UIP, right? And we're going to say that because of this, we know that together with the things set at earlier levels, A, B, and C, that Y would therefore have to be false. So we learn a new clause, and the new clause we learn is, better than that. The new clause we learn is not A, or not B, or not C, or not Y. And we add that to the clause database. Okay, and that turns out it's easy to do that with resolution, and it's easy to analyze the so-called conflict graph to figure this kind of stuff out. So that's the way these things really work under the hood, is by this kind of method. Like I said, it's okay to ask questions. Okay, so let me see what changed. Almost nothing changed here. I think I already said all this stuff. Okay, so what's new here is here. We've learned the clause not A or not B or not C or not Y. We now backtrack. We backtrack by unsetting the decision literal X and everything else that was set as a consequence of setting X. But we don't backtrack so far that the values of A, B, or C change. So those remain true. And now from the clause not A or not B or not C or not Y, it follows that Y follows by unit propagation. So we set Y true at that point, and now we start unit propagation again and go forward in the same direction. So a little unusual feature of this backtracking is we entered this decision level by setting X true. When we backtrack, we don't set X false. We might set X false by unit propagation, or more generally, we might set some other variable like Y false by unit propagation. So it's not quite a traditional backtracking where you change your mind on the previous decision. You really backtrack and use the newly learned clause to help the search procedure go forward better. What's next? Actually, that's first end of part one of the talk, so it is okay place for a question, right? So propositional proof systems for SAT solvers. So I mentioned resolution, right? So in resolution, the proofs, they're really refutations because they prove something can't be satisfied, and they reason with clauses. Every line in the proof is a clause. If you've taken any kind of course in logic, maybe back in what Americans would call high school, you might have learned about using modus ponens and doing more general formulas, ands and ors and nots and if-thens and so forth, right? So if you work with that as a proof system, the kind of proof system you might work with as a human being rather than as a computer, that's what's known as a Frege proof system. So the Frege proof system is The lines are arbitrary formulas built up with ands, ors, nots, if, thens. Modus ponens is maybe the rule you work with. Everyone knows what modus ponens is, I think, right? From A and from A implies B, you infer B. I'm gonna write it down. I should have put it on here. From A and A implies B, you infer B. And this turns out to be a nice proof system. It's pretty powerful. It can prove any tautology. And then for the purpose of this talk, there's actually a unlikely sort of extension to this idea, is being able to introduce abbreviations for formulas on the fly. So maybe you've started a proof and you've got a formula in the middle of it that you're going to keep reusing it. So rather than having to rewrite the whole formula every time, you can introduce a new variable that stands for that formula. And so this is what's known as the extension rule. So I've got here on the slide an example of, from the formula x and y, I introduce a new variable u, which stands for that formula. So u is brand new, it hasn't been used anywhere. And we just say, let's from henceforth, u is going to stand for x and y, and we can use it in its place. And you can iterate this process. And this makes more sense in extended resolution to do this, because in extended resolution, you're limited to saying ands of ors. And this rule was introduced by Satan in 1966, who was studying the complexity of resolution and wanted to be able to work with formulas that weren't just in CNF form. So he introduced the extension rule as a way to talk about more complex formulas by introducing literals to stand for more complex formulas. So as I mentioned, resolution corresponds to CDCL, but it's also a very weak proof system. Extended resolution would be nice, is a very powerful looking system, and it's unknown how powerful. Let's leave that as an open question. I can answer that as a question if you want to ask it. But it'd be nice to try to bring SAT solvers up to using more of extended resolution. So that's where I want to go next. But before I do that, let me mention there's various other proof system. There's one other proof system that's going to come up, which is the DRAT proof system. And I'll talk about that first, right? Okay. And in principle, though, these proof systems have the same strength as extended Frege. There's a bunch of, just to give a little bit of a landscape here, what I'm not going to talk about is in small font on the screen. There's weaker proof systems like tree-like resolution and regular resolution. There's a huge number of intermediate proof systems, AC0 Frege, cutting planes, Null-Stellensatz, the polynomial calculus, sum of squares, MaxSat, which for maximum satisfiability. Some of these are based on computer algebra systems. And in general, there's a number of other algebraic proof systems which deal with equalities in various rings or fields or whatever, and semi-algebraic proof systems that deal with inequalities in various domains. So there's a ton of these systems. And then there's also a few systems. By the way, I put intermediate question mark here because some of these things have their strength known and not all, but many of them don't, right? And then there's a few potentially stronger systems of which I might mention arbitrary symmetry breaking, for instance. So there's a bunch of these systems out there. But I want to focus in on DRAT and then extended Frege for the CDCL. So, but first, let's do an example. Okay, so there's two examples here. First one is the Pigeonhole principle. Pigeonhole principle has a long pedigree of being used as studying the complexity of proofs. I don't remember, but I probably talked about it here in Prague before. I once gave most of a seminar about the Pigeonhole principle, a quarter-length seminar, not a semester-length seminar, but still I managed to stay busy talking about the Pigeonhole principle for 10 weeks or something like that. So there's a lot to say about it. But just the basic thing is, Pigeonhole principle is just a set of clauses which are unsatisfiable by virtue of the Pigeonhole principle. So basically, they're saying there's no way to make an injective mapping from n+1 to n objects, or pictorially or picturesquely thinking there's no way to have n+1 pigeons fit one-to-one into n holes, right? And so this is a set of clauses. The first types of clauses are the totality clauses. So for each I, we have variables p, I, j that says the ith pigeon goes to the jth hole, or f of I equals j. So the first type of clauses say pi1 or pi2 or ... pin, every I is mapped to at least one j. Written out explicitly as a Boolean formula, not a for all I exist j kind of thing, just written out as a clause. And the second type of clauses are the injectivity clauses that says that there's not two different values for I that go to the same j. So either not pij or not pi prime j, where I and I prime are different. So taken together, these clauses can't be satisfied by the pigeonhole principle. And so this has been studied for a long time, and I guess Cook and Reckhow back in 1979 showed that there are polynomial size extended Prager proofs of this. Hawken in a famous result showed that it does require exponential size resolution proofs. So this is the canonical example. It's going to be hard for CDCL to do, at least in its pure form. And I showed it has polynomial size Prager proofs. And I put a ... here on the citations because there's been a ton of work improving Hawken's results on lower bounds over the years, but I'm not going to talk about. But let's just see how the proof goes. So here's the extended resolution. I guess I should stay here, not point at the screen. So here's an example of how the extended resolution proof goes. So over here on the right-hand side of the screen, I've got a column of pigeons on the left and a column of holes on the right. And we think of arrows going from the pigeons to the holes, from left to right. And so here, for instance, this edge here, mapping from I to n, is true. Well, we have the variable pin that's true if that's part of the mapping, right? And we're going to take the pigeonhole principle on n plus 1 pigeons and n holes and throw away 1 pigeon and 1 hole. So we're going to throw away the top pigeon and hole. And we'll do this by following. If I is mapped to n, then we'll just take whatever n plus 1 was mapped to was j, and we'll now map I to j. So if we take out the top hole, the top pigeon, we take the image of I now that had gone to the missing hole now goes where the missing pigeon used to go. Okay, so one pigeon is blown away. If it wasn't from the last hole, we swap them around, right? And we can do this with an extension axiom or extension rule. Here, Qij is the new position for pigeon I. It's true if Pij holds, if it was in j, or if Pin and Pn plus 1 j held. Okay. And that takes us from the pigeonhole principle on n and n plus 1 holes and pigeons to 1 fewer hole and pigeon. And then you repeat that process until you end up with, say, pigeonhole principle on 2 pigeons and 1 hole, and then you can just prove that by brute force. It's very, 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 very simple at that point, right? Okay. And that's how the extended resolution proofs go. And you can see how this would cause exponential blowup in proof size because Qij involves 3 of the p's. So if you did this n times, you're going to get exponentially big formulas if you tried to unwind this, right? The other tautologies I want to talk about very briefly are the Satan tautologies. So this says the following. We have a low degree graph. Every vertex has a charge, a 0 or 1 value. The edges are labeled with propositional variables, and the clauses say that the sum of the truth values, interpreted as 0 or 1 values, on the edges instant to a vertex is equal to the charge on that vertex. So for instance, here is this hole labeled with 1 with 2 edges, x1 and x3 instant. So the clauses would say that x1 plus x3 mod 2 is equal to 1. And we would write that out as 2 clauses like this written here, right? And something in the middle, well, something with degree 3 would be 4 clauses, something with degree 4 would be 8 clauses, and so forth. Okay. So you write this out. So this is a tautology that you can't do this. So these clauses are unsatisfiable. And Alistair Urquhart showed that for a connected expander graph, that Satan principles require exponential size, resolution, reputations. It's true also for grid graphs. So in particular, these things don't have short CDCL proofs. On the other hand, they do have short extended Frege proofs and even polynomial size Frege proofs. To be honest, I put a approximately me in 87. I didn't prove anything of the sort then, but the methods I used made it immediately clear had you asked me at the time. Okay, so those are the two things I want to mention. I don't want to go into the details of the proof for now, though. So part 3 of the talk then is DRAD and propagation redundancy. Again, questions are okay. So now I'm not going to give citations nearly as well as I should for this section, so I just threw in a ton of them here to be ice virtuous about it. Okay, so I'm not going to try to cite everything exactly. These are proof methods for extending CDCL. They were originally intended for allowing the checking of proofs. So if you have a resolution, if you have a CDCL solver, these have evolved to be big programs, thousands of lines of code or more, simplistic in many ways, but combining many methods, and they tend to be buggy if you're not careful. So it reached the point where you really had to have a proof verifier, not only to make anyone else believe you'd prove something, but also just to make you believe your program was correct, right? So these kind of things were introduced as proof checking methods, where a SAT solver would be required to either give a satisfying assignment, which could be checked explicitly, or to give out a proof that could be checked explicitly. But it turned out that to make this work well, you had to go beyond resolution, because there's certain things SAT solvers do that aren't part of resolution. And then it turned out the natural way to do it had the full strength of extended Frege, a little bit surprisingly, perhaps. And so one thing is that we are able to now infer non-implied clauses. So you can infer clauses that aren't logically implied by what you've got so far, which is a little bit unusual, but we'll see what's going on with that. Before I do that, though, just mention that this has been the source of what's the largest mathematics proof ever. I think this is still the world record for proof size. Hoyle, Coleman, and Merrick some years ago proved the Boolean Pythagorean triples problem that, which is a relatively famous open question, showed that for every 2 coloring of 7825 numbers, well, the first 725 numbers, there's a monochromatic Pythagorean triple. A Pythagorean triple is a triple of numbers x, y, and z, such that x squared plus y squared equals z squared. And so that when with 7824, there is such a coloring, 7825, there is no coloring that avoids monochromatic Pythagorean triples. So their proof size in raw form was 200 terabytes. It was compressed down to 14 terabytes straightforwardly, and then with special encoding, they got it as low as 68 gigabytes. The running time was 37,000 CPU hours to generate it, 16,000 CPU hours to check it. It was on a parallel machine, so that was the net time was 2 hours, but on a bunch of machines doing the work there. It was open before that, yes. Oh, the history, I mean, for probably decades. I don't know how. I think it was an Erdos problem even. I'm not. It was, yeah, reasonably conjectured to be true for any n, right? I don't know about believed, but yeah. But yeah, no, this they resolved it. And they got very lucky because, as you can see, that had it been a little bit bigger, they would have been beyond the power of the solvers, right? And they had to invent a number of new techniques to chip away at this. So if you get a factor of 10 improvement in the runtime, that might make the difference between solving this and not. But with exponential runtimes in general, of course, it doesn't get you very far, right? But they got lucky and picked this up. There's been a number of results of this type. I think this is the biggest one, though, right? Yeah. So, and I think you can download it if your computer is big enough and check it if you believe the checker. Yes, Andrej. I don't know, actually. That's just what it said in the paper. I don't know what the special encoding is. That was the question. Yeah, I don't know. What's a little unusual is, yeah, sorry, Neil. I don't believe this particular proof has been shortened, but maybe we could get it down by a factor of 100. Might be nice. Yeah, why not? Yeah. Yeah, and some of the theoretical things that go into this was the cube and conquer method of breaking it into sub-problems and so on, and looking for symmetries. Well, there's not a ton of symmetries of this, right? That's another thing that's very important for these types of problems. And a little bit unusual, had this particular problem, the verification was about half the time to generate the proof. But in fact, frequently and typically, the verification time is longer than the time to generate the proof, double, triple, or even 10 times longer, just because the proof is somehow very focused. Generating the proof is very focused on things, and the output from the proof doesn't really explain what kind of things were pruned away during the process very well. So, you know, and nowadays there's an annual SAT competitions, and they routinely require that SAT solvers have to output a proof of the correctness of something being unsatisfiable using these kind of. Oh. Oh, let me see. Every two coloring of what I said. No, I think it's okay. Every one up to 7824, there are colorings up to 7824 that avoid monochromatic Pythagorean triples.
I thought you mean every two coloring will put each member of the.
Okay, good. Yeah. Yeah, 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 it certainly is, yeah. For the four color theorem used different methods, yeah, that kind of thing could be reattacked from this point of view, I guess. There's been a number of other problems like establishing the values of Schur numbers, getting proofs of the Ramsey numbers, and this kind of stuff. There's a lot of work going on in different aspects of this kind of stuff. Yeah, it can be lots of things. Yeah, it can be lots of things. It doesn't have to be such straightforward combinatorial problem, right? Okay. So, at any rate, back to DRAT, propagation redundancy. So, the actual definition of DRAT is super confusing, and so I'm going to spare it for you. So, I'm going to try the easier definition of propagation redundancy, which is a stronger notion. So, propagation redundancy, you start with a formula, a CNF formula gamma. What's going on with my? That's weird. My pen has stopped working. That's very disturbing. Okay, so I could use the blackboard. I want to mark on the screen. Oh, that's weird. Oh well. At any rate, I'll just say words. In the boldface in the middle of the screen, we start with a formula gamma that's satisfiable, and we want to add another clause C that doesn't follow logically from gamma, but doesn't change the satisfiability of gamma. So if you add C, of course, you can't change an unsatisfiable thing to satisfiable by adding another clause, but you might change a satisfiable thing to unsatisfiable. And we'll add this in a way that doesn't change that, right? And so with I'm very disturbed that my pen's not working. Oh, look at that. Got it. Okay. The tip became unscrewed. Okay, so here if we basically, there has to be a partial truth assignment tau, which assigns true-false values to some of the variables, such that from gamma and the negation of C, which means add the unit clauses from the negated literals of C, they imply that gamma and C is true under the assignment tau. So tau is changing some of the values of variables, but we're saying that if gamma holds and also not C, then under this changed value, gamma holds with C. So if gamma is satisfiable and C is false, you can modify it to make gamma satisfiable with C true. Okay. And this subscript 1 on the implication means that for every clause D on the right-hand side, the CNF gamma with not D yields a contradiction by unit propagation. So this can be checked very easily. You just, well, at least in polynomial time. You take every clause on the right-hand side, you negate its literals, you throw them in with gamma, you unit propagate. All this happens in polynomial time. So it's a checkable condition, in other words. And just to say very briefly, there's a SPR, subset PR requires the domain of tau to be the variables in C. Okay. So this is an example of an inference where you could derive something that doesn't follow. And this type of inference is very useful. It's a little stronger than DRAT or RAT for short, but it's a lot easier to explain what's going on. Okay. Yes. Oh, yeah, the rule is sound, it just implies. So the only purpose for the unit propagation there is to make it polynomial time checkable. Right. So yes, that's a great question, right? And then there's Neil Toppin and I came up with a stronger version of this known as subset propagation redundancy, or maybe subset redundancy, but SR for short, because SPR was already taken. Which is now, instead of having tau be a truth assignment, sending variables to true false values, we make it to be a substitution that replaces variables with literals. So we might replace X with a literal, not Y, for instance, or something like that. Okay. And then this other than that, it's the same thing. You just say you assume that gamma and not C, they have to one imply in this sense gamma and C under the new substitution. So this is another thing. There's also, you'll notice a lot of times they're DRAT or DPR, DSR. That allows a deletion rule where you can delete clauses as well as add new clauses. And of course, deletion never changes satisfiable to unsatisfiable, so it's at least sound in the sense of proving unsatisfiability. But first of all, deleting things can make more things be deducible by these PR and SR rules. Also, deleting things makes the unit propagation faster and makes proof verification faster because there's fewer things to check for unit propagation. So that's why you would delete things. But just that's sort of orthogonal to my lecture, so I don't want to dwell on that. So interesting is this goes back essentially to Oliver Kuhlmann. The extension rule can be simulated by this PR rule. So the extension rule, suppose I want to infer U if and only if X or Y by extension. So U is a new variable, it's going to stand for X or Y by extension. Well, to add the clauses not X or U and not Y or U, we can use the truth assignment that sends U to true. It's that simple, right? Because if you send U to true, then you clearly made those two clauses true. And you haven't falsified anything else because U doesn't occur anywhere else. And then to infer not U or X or Y, you just use the truth assignment that sends U to false. And you can check that this also works fine. It doesn't falsify anything that was true before. And it clearly makes not U or X or Y true because we made U false, right? Okay, ta-da. Okay, in this setting, it's really trivial. In DRAT, it's actually harder to check this, but at any rate, let's let it go, right? And then the converse holds too. Extended resolution simulates propagation redundancy and substitution redundancy and so forth. Again, I've got an approximate equals there because that result is older than the definitions of these systems. So, but essentially, right? So these systems are equivalent to extended resolution and strength. And they were designed to be usable by CDCL solvers, right? So just as, let me just say this slide very quickly. One disadvantage of it, well, I should actually go into this. One disadvantage of extended resolution is that it complicates proof search a lot because CDCL proof search just went by setting variables true, false, and doing unit propagation. For extended resolution, or in general for PRSR, there's the question of what new formula do we introduce an abbreviation for? We're gonna have U if and only if some formula. What's that new formula? Well, many choices, right? Or if you're inferring something by DRAT, what's the formula you're going to infer, right? So there's a lot of choices involved there. One way to make this at least restrict these choices is to disallow new variables, right? So we say that we can't add a new variable. So thus it looks like we can't simulate extended resolution. Looks like, it's an open question, right? And then the systems come with these superscript minus signs to mean the variations of the rules that don't allow introducing new variables. Okay, but on the other hand, Neil and I showed that at least the subset propagation redundancy rule, which was weaker in strength than PR, does have short proofs of all the sort of classic hard problems for constant depth Rager proofs. I'll just say that. A lot of the classic hard problems that are hard to prove in low-level proof systems all have short proofs in these systems without new variables. And this includes the pigeonhole principles, which were done earlier for different systems by other people. The bit version of the pigeonhole principle, where instead of having Pij that says pigeon I goes to hole j, you have the bits of the number j are given to you by variables. The Satan tautologies and various other ones as well all have short proofs. So for example, how could you prove the pigeonhole principle with substitution rule without new variables? We're just going to do the following. We want to infer the unit clause as not PIN, which says that pigeon I does not go to hole N. Remember, that's what I removed before, right? I got rid of hole N. So to infer not PIN, we use the substitution that interchanges pigeon I and pigeon N plus 1, right? And so if PIN is true, then we interchange pigeons I and N plus 1, thus making pigeon N plus 1 go to hole N. And then we basically discard the last pigeon and last hole, and we repeat. I hope I haven't oversimplified this, Neil, but you'll correct me afterwards if I did. Okay, so that's an example of how you would prove that. Okay, so on to the last topic of the talk. This is more speculative. It's very new work. We've just done this the last few months. The goal here is to try to directly put extended resolution into a CDCL solver. And as I mentioned, the problem is, how do we pick? We're going to introduce a new variable u that stands for some other variables x and y. How do we pick the variables x and y? So we're looking for some method for this. So I'll show you pictures in just a moment, but we're going to use a method known as the dual implication point method. It's going to generalize what I earlier called the UIP, the unit implication method. Dual implication point generalizes unique implication point, sorry. It's a pair of variables x and y that together with literals from a lower level imply a contradiction. I'll show you a picture in a moment. These appear all over the place in conflict graphs. There can be a lot of them, quadratically many, but there's a nice linear time algorithm to identify all quadratically many such choices based on an effective version of Menger's theorem. And there's been a little bit of prior work back in 2010. There's a system glucose ER that I'll mention a little bit more because it has some very interesting properties. And another system, Tiny Sat, also from 2010, that have attacked this head on the way we have. But somehow since 2010, nothing's happened. So we're coming back to this. And I think we've got also a very flexible method, as you see, that gives a lot of things to explore. So at any rate, here's the picture. All right. I worked pretty hard on this slide, so please appreciate it. Okay. This part's in the paper, but okay. So here I've got a conflict, right? I've got a decision. See, there's a decision variable here, x1. There's a conflict here, a falsity. And all this is going to disappear when I change slides in a second. And there's a UIP is x5 here in the middle. And we're looking for pairs of variables out of the conflict graph to pick as the DIP. So question. So I didn't actually say, from the previous, I didn't say very well. The previous slide, the UIP was that variable y. And we used the conflicts you know, I can probably go back to that. Not very quickly, but I think worthwhile. We use this dotted line here to separate the UIPY from the conflict, and the dotted line crossed the UIP and the variables A, B, and C coming from lower levels. And so because of that, we said that if you set Y false, set Y true, A true, B true, and C true, those by themselves were enough to imply falsity. So we thus learned the clause, not A or not B or not C or not Y. And then we backtracked because U was a unique implication point. It was the only one at the top level. And so when we backtracked, we set Y true just by unit propagation. So that was the whole point of that back. So thank you for asking that question. I didn't explain that very well earlier. Okay. Right. So yeah, Neil's completely correct. Probably not everyone heard, but this is one of many possible ways to cut a graph. I mean, you could cut the graph here, for instance, and learn not V, not U, not B, not C, right? Which would be also a clause of size 4 right there, which on the face of it might look as good, but then we wouldn't get that asserting property. So there's many possible ways you could cut this conflict graph to learn new clauses. The UIP one is what everyone's settled on and seems to work the best in many situations. Okay. Okay, here's the disadvantage of being on an iPad. Whoops, went too far. Okay, so back to here. So the UIP has the property that all paths starting at conflict, heading back to the decision variable, have to go through the UIP. Okay, so we're looking for pairs of vertices that every path has to go through one of them. So the first pair to look at here is x1, x3. You can check that every path starting from falsity has to go back through x12 bar, not x12 or x13. So this is the first choice then. Well, it's just here, I don't need to circle, it's in red. We can pick our new extension variable z to stand for the and of those two things. And then we can learn two new clauses, not z, because there's no lower level literals coming in there. And then this other big clause here, which is that if, let's see, it probably says if y3 is false and y4 is false and y5 is false and y6 is true and z is false, then x5 is false, I suppose, or z is true, whichever way, one of those things. It's okay, right? So basically we're getting two clauses there, one after the DIP and one before the DIP. Or we can go to the next one we can look at is here is x11 and x13 form a blocking point. So we can introduce new things there as well. And now you can start to see the pattern, x11, x10 bar, they block all paths. And I'm talking about paths at the top level. The lower level things are there in blue, so we're not really counting those paths. We're just letting those be side variables that aren't going to get unset at the present. The top level ones are the ones that are going to get unset at the present. And finally, here's x11, x9, and this one has maybe we can do the next one, x8 and x9 bar. So here we have rather substantial clauses that could be learned with Z. And one of the advantages to this is, first of all, we have just two literals there. That's what the DIP does for us. We're looking for these two blocking points. The learn clauses involve Z both positively and negatively. So that improves the chances that Z will be useful later on in unit propagation. In fact, the whole point of introducing a new variable like Z is to use it in the future in unit propagation. If we don't ever use it in unit propagation, it won't ever enter a conflict graph. It'd never get used for anything else. So if you introduce something that doesn't get used in unit propagation, it's worthless. So one of the motivations here is to introduce something that'll be useful for unit propagation. Now, we do know that Z was introduced as Z implies X, in this case, X8 and X9 bar. So we do know that Z certainly implies something. And from this second clause here, we know there are things that imply Z, right? So we want at least things, whoops, that especially should be in typo here. I added this at the last minute and got it backwards. The especially should probably move in front of positively instead of in front of it negatively. Okay, so we have things that imply Z, right? So that's the motivation here for this. And as I said, this is very recent work. So we've run a number of experiments now. There's more planned, but we've tried different examples. This is just for experts really of which DIP to pick. And we pick random ones. There's many, as I said, there's quadratically many in general. So we pick one near the conflict, one in the middle, one near the end. We pick them at random, that kind of stuff. Middle seems to work sort of best. And middle means we find two paths, we pick the middle one on that path, and then we pick the middle one that's available for that one. Doesn't really matter here. There's various things we can filter by how frequently the variable has been used recently. That's the activity. How many levels are involved? That's the glue. There's a lot of DIPs come up. And so we tend to make sure the same DIP comes up 5 or 20 times before actually picking it. And experimental results are that it performs very well on the Zeiton principles, random XOR formulas, and another strange class I'd never heard of before, intersecting interval tautologies. It doesn't seem to work more well on the large universe of other problems that are considered in SAT, but I think it still has a lot more to look at that. Interestingly enough, this old system from 2010 of glucose ER turns out to work pretty well on these particular ones as well. So that's an interesting phenomena. They had a much less flexible way of dealing with introducing variables by extension and did it in a different way. So it's definitely interesting to look more into why that works. And since I'm running out of time, just mentioned there's a bunch of open questions. Let me just say, obviously we need to explore how well this works. That's the first point here. Can explore more across a wider range of SAT problems. Is the DIP-based extension system capable of simulating full extension resolution? I don't know, because there's this very structured way of introducing variables by extension that's allowed. Does that enough to actually get full extended resolution? It's still open. Also, oddly enough, in practice, we get very short proofs of the Zeiton tautologies. They're like polynomial size, almost linear size proofs. It takes slow growing exponential time to find those proofs, but the proofs that result are rather small, which is very encouraging. We know they're small proofs by extended resolution, but the fact that the program can find it is very encouraging. But the weird thing is we don't know how to construct those by hand. You asked me to prove a theorem that well, I don't know how to do that, right? And I've tried by hand, and sure, nice things happen, but I don't see the end goal of actually proving it by hand. So it'd be nice to know that. So and finally, there's a lot of other things I think DIPs could be used for as well, such as learning new to clauses and so on that hasn't been explored yet. That's the next to last point there. So I think I'm out of time here. So I'll say thank you again for inviting me to speak, and it's been a pleasure.
Thank you very much for a nice talk. I'm happy that it was done in such a way that even non-experts like me could follow and actually enjoy the talk. So thanks a lot for that. Other questions? We had some during the talk, please.
Sam, can you hear me?
Yes, please.
What is your opinion regarding SR minus, whether it can simulate extended resolution?
So I mean, okay, that's a good question. So whether this substitution redundancy principle without new variables. So we know it's very powerful because already SPR minus is very powerful. I think it's too much to expect that it can simulate extended resolution. It's probably an outside chance that it could simulate Frege's proof systems. But I mean, you can ask Neil as well, but I have no idea how to prove it either way. We have lower bounds as an open question here for the RAT minus system, which is the inference I did not define without new variables. And that's the best we have so far. I suspect that those are not super proof systems. Along the same question for the audience who probably doesn't know it, it's open whether these strong proof systems like Frege or extended Frege have polynomial size proofs for all tautologies. If they do, then NP equals co-NP, but it's completely open to give even explicit examples of tautologies that require Frege proofs that require more than order n squared many symbols. So just like the PNP problem, very open questions about complexity. For proof complexity, there's very much these very basic open questions about lengths of proofs that we don't know. Yeah.
Quick question. Is it true that
is this true that all the proof systems you're interested in, they are basically, if you don't care about size, they are complete. They can prove, right? All of them
Yes,
basically can prove all tautologies. So it's only question of size.
Yes. So yeah. So every system I mentioned in the talk is complete. Yeah.
All right, thanks a lot. Any other question, comment? Yes, just I give you a mic, just a second.
Oh, so the Satan principle is a kind of parity principle. So you're looking at, it's proved by noticing the following, that the total charge on the nodes is odd, and that each edge has two ends. And so if the Satan principle clauses are all satisfied, there'd have to be an odd number of positive edge ends, right? So it's a kind of mod 2 counting. You take the sum over the nodes, and that comes out to be 1 mod 2. You take the sum over the edges times 2, and that comes out to be 1 mod 2. Can't happen, right? So that's how we prove it as a person. So there's a pigeonhole principle, of course, as we prove it as a person rather than a computer, as we count. So one of them is sort of counting mod 2, and the other is counting. And I don't think there's any direct relationship known between these two things. There's various parity principles that work of Itai and so forth many years ago separated between proving parity from pigeonhole principle and pigeonhole from parity, but I don't think that's known for Satan tautologies. Pavel might. No, he doesn't know either. Okay. Yeah.
All right. Any other question? Anyone? Yes.
So thanks for a very nice talk. If someone like me, total non-expert, wants to try my hand at using practically a SAT solver, is that something that I could do?
Yes. So if you want to try to practically use a SAT solver, there's a variety of them available. If you're comfortable with Linux, even a little bit of command line, download Catacall or KissSat. These are the two modern ones that probably work the best. And you can type make, and then you can use this very straightforward format for entering in instances of SAT. And so, you can run it very quickly and get results. Easily, maybe not always quickly, but easily, right? If you want to write your own stuff, as compared to just play with existing SAT solvers, again, there's annual SAT competitions, and some of them are specifically designed for people who make up to 1,000 lines of change in Catacall, for instance. So if you have some idea, some tweak to a SAT solver, you're sort of encouraged to sit down and tweak the existing source code. Most of them are open source, and so it's mostly available. That said, it does take a little bit of effort. Coding always takes a lot of time, right? So, but if you just want to try running it, you've got your favorite tautologies you want to run it on, that is quite easy. Okay.
Is it, if you really start playing with it, is it difficult to come up with something which would actually make the life difficult for the solver? If you just try to come up with random, or if you really on your computer start playing with it, is it easy to make the life hard for it or not?
Yes, it's easy to make life hard for it. Random clauses tend to be very hard, for instance. Just choosing them at random. You can easily find, but here's a good example. Take a large integer that's a product of two primes, make up variables for the intermediate gates of a circuit that multiplies the two primes together and produces that integer, leave the inputs unknown, and then ask it for a satisfying assignment, which would factor the integers. Okay, for instance, that would not be easy to code up maybe, but it's straightforward to I guess, conceptualize, right? Okay.
Very nice. Any other comment or question? Neil.
So this SAT competition plays a big role in the SAT solvers that people work on. I'm just wondering if you can say something about that and say something about the kinds of instances that people care about based on what appears in the competition and how it compares to what you're looking at here.
So good question. So the ones I've mentioned here have been very combinatorial, and these tend to be, so these typically are very hard for SAT solvers. So the Pythagorean triples had only, was it 75, 28 variables? That's a pretty small thing. I was playing around recently with some things that Marijn Hoyle has posed about the so-called Folkman graph, and that has only 700 and something variables, and it seems to be impossible to solve. The industrial problems tend to be huge. Someone has some aspect of software verification or hardware verification. They'll have hundreds of thousands of variables easily, and those turn out usually to be moderate, not often. They often are easy to solve, maybe only an hour or 2 hours, like that. Scheduling problems are probably usually smaller, often quite solvable. Let me see. Now I'm missing the gist of your question. Will my new algorithm? So right now, the new algorithm will just basically well, okay, we're dealing with we're not dealing with the best one. We built it on top of a solver, X MapleSat, that's not the best solver. So comparing the X MapleSat with our extensions to the one without, overall we run slightly slower. We're a lot better on some. All this work with the DIPs adds around 2% overhead to the runtime. So that chops off some of the solution. But the nice thing is we actually have some very good criteria for when the DIP-based method is helping. If the new variables that are introduced by extension are used as decision variables a lot, like 10% or more, then they tend to help a lot. If they're not used very often by decision variables, then it tends not to help. So as a first heuristic, we've just tried turning it off. We run it for a while, and then if it's not generating more than 10% or whatever the threshold was, or decision variables being variables that were introduced by extension, we just turn off the DIP solving and say, okay, go run, right? And that end result means that we cut the overhead down a lot. So in other words, either our method works or it gets out of the way and doesn't hurt very much. Okay, so that's sort of encouraging too, yeah.
Thank you. Further questions? Pavel.
No, I wonder if these very efficient SAT solvers are used in these large language models which simulate artificial intelligence.
Okay, our LLMs used, our SAT solvers use LLMs. As far as I know, none of these type of SAT solvers are used in LLMs. These SAT solvers are used, or the basic ideas behind them are used for the so-called SMT solvers, which some of you may satisfiability modulo theory, which are used for software verification a lot, for instance, in the Z3 system. So the methods are used in that kind of setting. I don't believe any LLM uses this. Many people are trying to use LLMs for theorem proving now, and I think most of the emphasis that I've heard about has been using it to work with proofs in lean. But whether LLMs could help SAT solvers by choosing decision variables, I don't know that that's been explored yet, but I'm sure someone's thinking about it, right? Okay.
Thank you. Any other question? Just a second, please.
That's your, how to say, you also work with the lean system.
Oh, do I work with a lean system?
Yeah.
Personally, I had a student who worked with it, and I learned a little bit about it. And I may work in the future, but I haven't really worked much. This.
Yeah.
Oh, this. No, this doesn't work with this does not work with lean. No, so lean does not involve SAT solvers, as far as I know at all, right?
Yeah.
Okay.
Right. Anyone else? Okay, Ivan.
Thank you. So again, total non-specialist in this, but in this theory, you for sure have some rule of thumbs or theorems, whether not to how to actually find a resolution, but to see if the system is resolvable or not. Well, I'm working in continuum mechanics, for example, and from engineering point of view, it's always easy to write some sort of law, physical law, which would glue together two completely different rules for material. So you would end up with something like a system where you have a hard switch between two completely different laws.
Mhm.
So which would resemble the problem like this, but like what we were talking about, but with continuum amount of conjectures you need to satisfy. Could you, is it possible in principle to offer some insight on whether from the logical point of view, these sort of systems with continuum amount of logical constraints to be satisfied would be possible? Like if it's.
So you're, okay,
Thank
so you're talking about, let me make sure I understand the question correctly. You're not talking about a continuum number of methods to apply to SAT. You're talking about a continuum set of clauses. Yeah, oh, that's an interesting idea. So rather than having discrete clauses, you have some continuum set of clauses, yeah. I'm wondering, I don't know whether, maybe some of the cutting planes, proof systems that deal with linear inequalities could deal with that, but I mean, this sounds like an unexplored area to me, I guess, really. Yeah. I don't think I have any good insights on that, right? So, but yeah. Yeah, I'm not sure. There might be something there, I just don't know. Yeah.
Okay, okay. Any other question, comment? I don't see any. So it seems that we exhausted all the urgent question, some is being here around, so you can further ask him or consult him if you are interested. And at this point, I'd like to thank him again for very nice talk. Thank you.
Thank you. Pleasure.
Yes, and I would like to thank all of you for coming and being here with us today. Thank you.